To this afternoon's lecture. So, go with that. Right. So this afternoon, we're going to be talking about two very, very special libraries within Python, known as NumPy and Pandas. And we're going to start talking about NumPy. I think NumPy, I believe, is a little bit harder to understand than Pandas. So we're maybe starting with a slightly more difficult one. They've both got their sort of own advantages and disadvantages. But NumPy and Pandas are both very, very important if you're doing anything scientific, which you will be if you're doing modeling within Python. So NumPy has a number of features that basically allow you to very easily work with large multi-dimensional arrays, and I'll come back to that in a moment. But when you're working with these large multi-dimensional arrays, it allows you to do it much, much more efficiently than if you were trying to store them in some of the conventional iterative structures such as lists. And that becomes quite important when you're doing much more complex things, which some of you may well be in your projects, because computational efficiency becomes more and more important the more you sort of add in. And that's one of the reasons why NumPy is particularly important when you go on to work with machine learning, for example, as you'll see later in the course when Mike talks about machine learning and when I start talking about AI-based natural language processing. Now, NumPy and Pandas are already included in many scientific distributions of Python, such as the Anaconda distribution that you've all got installed. And that's part of the reason why we recommend the Anaconda distribution, because it's already got these really key libraries already installed, so you don't have to install them separately. So we don't need to worry about doing anything other than importing NumPy and Pandas into our code. Now, there are conventions around the way in which we set up an alias. Now, you saw this morning that when we opened a file, we used the with command to do that, that we said with open and then our file name, etc., as f. And that's what's known as an alias. We're going to say, with that thing, I'm now going to refer to that thing now as f. We can do the same when we import libraries. Rather than just saying import NumPy or import random, we can say import NumPy as NP. And then whenever I want to refer to NumPy, I now just say NP, and that means NumPy. And it's quite an important convention that's used for NumPy and Pandas, that they are imported with these standardized aliases. So NumPy should always be given the alias NP. So whenever you import NumPy, it should be import NumPy as NP. And then whenever we refer to NumPy, we say NP instead. The very hardcore coders will shun you from their club they'll probably club you over the head if you don't take to this convention. It's very important in the coding world. Import NumPy as NP. So the main object in NumPy is the multi-dimensional array, which all sounds very mind-blowing. But as with all things in life, multiple dimensions make things much better. So before I try and explain NumPy, I'm going to first of all try and explain what we mean by a multi-dimensional array, because it can be quite difficult to get your head around this. But this is essentially the reason why NumPy is so useful. So let's first of all consider a one-dimensional array. So at the top here, I've got an example of a one-dimensional array. And you've been using these lists, essentially, a list of numbers. That's an example of a one-dimensional array. We've got one dimension of values. Okay. Now it could be that those values represent different things, and we'll come on to that in a moment. In fact, actually, let's come on to that now, because it might be a little bit easier to explain. So let's think of some practical examples for multi-dimensional arrays. So in a one-dimensional array, that could represent a list of ages. So we may have a list of ages of patients, for example, And that list of ages is single dimensional because the dimension is age. Now we can also have two-dimensional arrays, and an example of a two-dimensional array might be a list of ages for each group. So we may have three groups, and we've got ages for those groups. So we've got two dimensions there. We've got the ages and the groups. Now you're all used to two-dimensional arrays, even though you probably don't think about them as such, because you're all used to using things like Excel and tables and things like that. That's just a 2D array. You've got essentially columns and rows. Okay, so you've got age as one dimension in this example, and different groups being your second dimension. So then we start to get a little bit weirder, because then we think about three-dimensional arrays. But if you think about a three-dimensional array, obviously a three-dimensional array, trying to visualize anything in 3 dimensions on a 2D plane is difficult. So it's better to think about something slightly differently. So imagine, to take our example of lists of ages, let's imagine that we wanted to store the lists of ages for each group within each department. We've now got 3 dimensions of information. We've got the ages, we've got the groups, and then we've got departments. So in order to specify any one of those individual ages, I would need to know both the department and the group, and then the particular age within that group would be that unique value. So you've got 3 dimensions that specify exactly where that point is in our 3-dimensional array. And of course, you could, to really blow your mind, go far beyond 3 dimensions, which is where it starts to get much, much harder to try and visualize, because it's very hard for us to, as humans, to understand anything beyond 3 dimensions. But of course, if we think about it in these terms, we could imagine a 4-dimensional array that had different hospitals with different departments within which there are different groups, within which there are different ages. And so that would be an example of a 4-dimensional array. So the point is, if you try and think about a multi-dimensional array in those kinds of terms, in these kind of practical examples that you will encounter every day as analysts, hopefully that makes them a little bit more grounded in your head, rather than trying to think about them as, you know, sort of multi-dimensional matrices in terms of a much more visual way of representing. But essentially, that's what they are. Your dimensions are the number of dimensions are the way in which you're drilling down to a particular value. So if you've got a 4-dimensional array, you could have a particular hospital, which and a particular department within that hospital, and a particular group within that department, and a particular age within that group, within that department, within that hospital. Okay, so that's essentially what we mean when we say multi-dimensional arrays. So you can probably already start to see that these might be quite useful for when we're storing real-world data, because actually there are lots of examples where we would want to store things in that kind of multi-dimensional way. So how do we do this in Python? Well, fortunately, declaring a NumPy array in Python is very easy. So we must remember to always import NumPy as NP. Remember, always NP. And then to set up a new array, new NumPy array, we simply give it a name, and then we use the NP. Remember that we're using that as our alias for NumPy now, dot array. So we want a new NumPy array. And then in this example, I'm giving an array that I'm storing into A. So in this case, it's a 1-dimensional array with 5 values in it. So A equals np.array, and then I open my brackets, and then the argument I pass into that is the list of values that I want set up as my array. So A is now stored as a NumPy array. Now, if we wanted to create a multi-dimensional array, what you'll very often find yourselves doing is to essentially create that multi-dimensional array from a series of lists. So let's say we had a 2-dimensional array, which, if we think back to our example, that would be, for example, where we had the list of ages for each group. So we may have separate lists representing the ages for each group. And then we can set up that multi-dimensional array simply by saying a equals mp.array. And then the list that we're giving here is essentially a list of lists. We're saying, and it's made up of list 1, list 2, and list 3. And if we print that array now, you can see it is two-dimensional in that it's got essentially a list of lists. It is got these entries here, which represent, in our example, the separate groups. And then each of these entries representing a separate individual's age within that group. Now, so that's setting up an array. That's pretty straightforward to do. We can use the shape function within NumPy to find the shape of a NumPy array in terms of the number of dimensions, if there's 2 or more, and the number of elements per dimension. So let's look at an example. Let's say we've got an array here that is just a one-dimensional array with the values 1, 2, and 3. So if we called shape on that array here, then it would give us the number of elements in that array. Okay, list of 3 age values, for example. In a 2D or more array, if we call shape, it'll essentially give us the number of rows and columns in multi-dimensional space. So again, let's think back to our grounded example. Let's imagine we've got a 2D array, list of ages per group. So we've got 2 groups and 3 ages per group. If we call the shape on that, then we'll get 2, 3 come out as the output. That basically means 2 groups of 3 age values. Okay. And then we could do the same in 3 dimensions. So we've got a 3-dimensional array here, where we can imagine having each of these lines represents a particular department, and then individual groups within that department, and then individual ages within that group within each department. We call the shape function on that, then we'll get 2, 2, 3 come out, which basically means 2 departments, it's the outer dimension here, with 2 groups in each, and each of them contains 3 age values. Okay, so it's always quite nice to think about it in those terms, because it'll help you think about what this sort of thing is representing, particularly for the kind of real world stuff you're going to be doing. If we want to find out the number of dimensions within a particular array, a NumPy array, we can use the ndim function. So if I've got an array here, this is clearly a 3-dimensional array, as we saw before. So this is, again, imagine 2 departments with 2 groups, each containing 3 values. Then that's obviously a 3-dimensional array. So if I use the ndim function and print that out on array C here, it'll output the value 3. Now, there's a really important thing that you need to be aware of whenever you're setting up NumPy arrays. That is, they need to be homogeneous. And what we mean by that is that you have to have the same number of columns in each row. So if we think back to our example, for each group within each department, within each hospital, if it's 4-dimensional, we have to have the same number of age values. Okay, so this, what you can see on the screen here, is an example of a 2-dimensional array where we've got one group that has 3 age values and one group that only has 2 age values. Now that's not really valid. That isn't, you can't have a NumPy array like that. However, just to add a little bit of confusion, if you wrote that in Python, it would not throw up an error. What it'll actually do is NumPy would store references to 2 separate lists within one big overall array, and it will give it it'll make it a 1-dimensional array with 2 references to 2 other lists. Now that's probably not what you want, and it certainly wouldn't allow you to use all the swanky features of NumPy, which is the whole point of doing this. So be very careful with that. It's not going to stop you doing that, but you absolutely can't set up a proper NumPy array if you've got different values. You would want to think about how you're going to deal with missing values, but you need to have something that represents those missing values. You can't have a different shape. You have to have the same number of values all the way through. So let's start talking about things that are useful to do in NumPy. Well, one of the things that's really useful is we can do mathematical operations really easily. So let's imagine that we've got a NumPy array, just a simple one-dimensional NumPy array that has the values 1, 2, 3, 4, and 5. And let's imagine that we want to double the value of every element in that array. We can simply, once we set up our array, so I've got it stored as the value a here, I can simply say a times 2. And if I print that out, you can see array A is now doubled for each value. Now, of course, you can do that pretty easily with a list, but the advantage, of course, in doing this with NumPy is A, it's much quicker, and B, it makes it much easier to do it multi-dimensionally. So if you needed to do that with a 7-dimension array, for example, it's much more computationally efficient to do that using NumPy. And so you can simply say double everything in the array, and it'll do that very efficiently. So slicing is also a really useful feature of NumPy, because it may be that we want to carve up various bits of our NumPy array so that we're only dealing with certain sections of that array. So let's imagine that we've got a 2-dimensional array. So here's an example. We've got 2 dimensions. We've got a dimension 1 here, containing the values 1, 2, 3, and 4, 5, and the second dimension here containing 6, 7, 8, 9, and 10. And let's say that one of these represents, I don't know, a particular number of admissions, and one represents the amount of time they spent in the department. And it may be that we need to double the value of one of these, but not the other, because the other represents something totally different. We can do that really easily using slicing. So here in our 2-dimensional array, what we can do is say, give me a new array called C, and I want that to be, so I use the square bracket notation here and give it an index of 1. Remember, we start counting from 0. So this will only give me that second dimension here, and it'll double every value within that, and that will be stored now in the array C. So if I were then to print out C, I'd get the array 12, 14, 16, 18, and 20, which is double all of this. But I've left this untouched. In fact, I've left the original array untouched as well. But I've only performed an operation by slicing out this second dimension here. Similarly, I might want to only print out the value in the third column of the first row. So if we imagine these are ages again, let's say I want the age for person 3 in group 1. So I can simply refer to that by giving the array name, and then use 2 square brackets notations here. The first specifying essentially the row, and the second specifying the column. So I want the 0, remember we start counting from 0. So on the first group 0, and I want the third value within that group, so that's index 2, and that will give me the value of 3 if I was to print that. So very similar to the way in which you saw about slicing up lists last week, and we can do the same thing with our multi-dimensional arrays as well. And remember, so the examples I'm showing you here I'm keeping them to fairly simple 1 and 2D examples for the most part. That doesn't really show off the power of NumPy. I will show you in a bit why you want to use NumPy. But of course, the power of this is you can do all of this even when you scale it up to dimensions you can only imagine. As well as doing mathematical operations, we can also perform statistical operations on our NumPy array really easily. So let's say, again, we've got a just simple 1-dimensional array here, numbers 1 to 5. Let's say I want to find the mean. I can just call the mean function on that array, and that will print out, it'll calculate the mean really quickly within that array, and it will give me that mean value. It might be, if we've got for example, a 2-dimensional array, as we've got here. So remember, group 1, group 2, lists of values for each of those groups. It might be that we want to take the mean across rows. For example, the mean of element 1 in each group the mean of element 2. So in other words, what's the mean of 1 and 6? What's the mean of 2 and 7? What's the mean of 3 and 8? So to do that, we call the mean function, and we give it the name of the NumPy array, and we specify axis equals 0. So that means do it across rows. You're doing it column-wise. Essentially, you're saying, give me column 1, the average, so 1 and 6. Give me column 2, 2 and 7. Or it might be you want to do it the other way. You want to take the mean across groups. You want to know what the mean of age of group A is compared to the mean of group B. In which case you'd use exactly the same thing, but you say axis equals 1, and then that would give you those means. So, and you can always check you've done it the right way, because so in the first example, we should have 5 values. If we print that, you can see that's exactly what happens. And in the second example, we should have 2 averages. We should have the average for this group and the average for this group. And that's what we get here. Another really useful feature of NumPy arrays is that we can easily take the dot product of 2 arrays. Now, for those of you who aren't familiar with dot product, when you're working with arrays and matrices, basically, dot product simply means take 2 arrays and then multiply the first element of the first array by the first element of the second array, and then add that onto the second element of the first array times by the second element of the second array, and then add that to the third element of the first array multiplied by the third element of the second array. So A dot B in this example would be 1 times 2 plus 2 times 4 plus 3 times 6, which would give us 2 plus 8 plus 18, which is 28. Now, you may be thinking, why on earth would that be useful? Imagine, for example, you were building a geographic model and you wanted to weight things according to travel time, for example. So one of your arrays may store travel time, and you want to weight things according to that. So weighting is a very good example when you want to use dot product, because essentially you're saying multiply this value by this weight. And anybody that's ever done a weighted average will be aware of that, where essentially rather than just taking the mean and assuming that each value contributes equally, you're saying, well, some values are more important because, okay, so we may have, for example, a geographic model where we've got 20,000 people living in one postcode sector and 2 people living in another. And let's imagine we've got a travel time that's pretty small for those 20,000 people, but pretty large for those 2 people living in another postcode sector. Now, we need to capture the impact for those 2 people, but clearly we shouldn't just take the average travel time by saying the average travel time for one postcode sector and the other, assuming that they're both of equal importance. What we should do is to say, but there are 20,000 people that this impacts here versus 2 here. So using dot product, we can do those kinds of calculations. We can use them for weighting, and that's particularly important for machine learning, as you'll come to see, that you're essentially multiplying things by weights, which determines something's importance to the overall calculation. So to do dot product in NumPy is really easy. You've got 2 arrays, whatever your 2 arrays are, and then we simply say np dot, and then give it the arrays that we want to multiply together, that we want to apply the dot function to. And then, so if I did that on these arrays here, you can see if I print dp, then we get the value 28. It's really easy to do dot product on NumPy. Now, it may well be that when you set up a NumPy array, you want to add more rows to your existing NumPy array. So let's think back. So rather than trying to think in terms of multi-dimensional rows and columns, let's now ground that again back in our thinking. So let's imagine we've got a 2D array here, and we've got 2 groups of each with 5 ages, and we've now got another group to add to our array. So the way in which we would do that is we set it up within this one-dimensional array here as a list, And then we simply use the vstack function within NumPy. So we say np.vstack, and then we combine them both into a single array here. So we say vstack, vertically stack is what it means, because you're adding a row. Vertically stack the array we had before and this new array that we've got here. So then it'll add this new array essentially to the bottom of the stack of rows here. And if we print that, you can see that's exactly what it does. It does values 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, which we had before. But now we've got this new group here, 3, 6, 9, 12, and 15. So that allows us to add another row, essentially. That's a vertical stack. And as you might guess, if we've got a vertical stack, there's also something called a horizontal stack, or H stack, which does exactly the same, but this time we're thinking in terms of columns. So if we think about columns in multi-dimensional space, what we're ground that back to our examples. So imagine we've got 2 groups with 5 ages in each, and let's say we want to add an extra age to each of those groups. So that's essentially adding another multi-dimensional column. So we do it in the same way. We give our column to add, but this time we've got to do it slightly differently. So before, with HStack, we simply gave it as a one-dimensional array because it's a new row that's going to be added. Here, because we're adding values to multiple groups, if we think about these things as groups, then we need to give them in itself as a multi-dimensional array. Essentially, it's a list of column values that we're going to add. So if we wanted to add 6 and 12 to the ends here, actually, I don't know why that isn't 11 if I'm following my convention, but anyway. So imagine we wanted to add the value 6 and 12. Then I would say add this value of 6, and that in itself is an array, and also add the value of 12 within an array. And this is all within a 2-dimensional array. So this is in itself a 2-dimensional array that contains 2 groups of values. It's just that there's only 1 value in each. But of course, you may want to add more than 1 column value. So maybe you added another 7 columns, in which case you'd have a series of 7 columns here and a series of 7 columns here. So a good way to think about that is that you want the list of values that you're going to add to each group. So here I'm just adding 1. Sorry, my iPhone is suddenly talking to me. I must have said something that resembles hey, you know who. Yeah, so the list of values. So here it's just a list of 1 value for each. And then I just use the hstack command to then add those additional columns. And again, the same way as before, we give it the original array and then the new array and tell them to horizontally stack, which again, if you imagine it in 2 dimensions, it's a horizontal stack because you're essentially slamming on another couple, or in this case, a single additional column onto your 2D array. And that's exactly what happens. So here, if we add 6 and 12, see 6 been added to the first group and 12 has been added to the second group. Now, as well as adding, we can also remove. Now, here's a function that I'm sure you would have all appreciated for a number of exercises up to now, the unique function. Yes, NumPy has a wonderful function built in that allows us to easily remove duplicate values for an array. So again, let's imagine we've got our 2-dimensional array here, 2 groups, 1, 2, 3, 4, and 5, and 5, 6, 7, 8, and 9. Now, in this example, we've got 2 groups, but there is an identical value within these 2 groups. Now, that might be absolutely fine, and indeed there will be lots of NumPy arrays and examples of NumPy arrays where you have duplicate values. Indeed, if your arrays represent ages within different groups, for example, you don't tend to remove people's data just because they happen to be the same age as someone else. However, there may be circumstances where you don't want duplicate values and you only want to deal with unique values. And so for those circumstances, you can use the unique function. So here's our 2D array. And if I want to, I could create a new array, or I could overwrite the array I've got. Let's imagine I just want to get rid of the duplicate values and overwrite this array with a version of this that doesn't have the duplicate values. Then I can just say b equals np.unique, and I'm going to pass into the input the array that I want to remove the unique values from, in this case, B itself. And then if I print B, it will only, oh, I didn't do that. It will only show me unique values. So it'll remove the value, one of the values 5 here. But let me just do that so you can see that. Sorry, I should have pulled that up. So let's zoom in. So I'll show you import NumPy as NP. Oops. Sorry, for some reason my keyboard stopped responding. It's very odd. Okay. So B equals np.array, and what do we have? 1 to 5 and 5 to 9. So I can then say B equals np.unique, and I'll pass in B. And now if I print B, I get an error. What have I done? Oh. There we go. See, it shows even when we're used to using this, we can still make mistakes. So if I now print B, you can see it's given me a single array, single NumPy array, that combines all of those values, but only in terms of unique values. It's transformed a 2-dimensional array into a 1-dimensional array, but which only contains unique values. So I've now got the values 1 to 9, and I haven't got a duplicate of 5. So that can be useful for getting just unique lists of things, as we saw examples of earlier, for example. It may be, for example, that we have an NP array that's got 3 groups here, so 1, 2, 3, 4, 5, and 6, and 1, 2, 3. And in this case, we've got an entire group that is duplicate. And let's say we want to get rid of that. We don't want an identical group within there. In this case, a row. So I can remove duplicate rows by saying np.unique, pass in the name of the array, and then if I specify axis equals 0 into that, that'll basically get rid of duplicate rows. If I say axis equals 1, it'll get rid of duplicate columns, and then we use values 2+ for 3-dimensional plus columns. So basically, we can get rid of additional rows or columns or multi-dimensional columns very easily using those functions. So the unique function can be really useful for that. Sorry, my slideshow's working. I'll have to do it like this. Okay, so this all sounds great. I'm sure you're thinking this, yeah, I kind of get this, but surely there's other ways. Couldn't I just do it, you know, as lists of lists of lists? And yes, you can absolutely do it that way. But there's a key reason why NumPy is better, and I alluded to it at the start, because it is much faster. So is it really that much faster? I'm going to show you now just how much faster this thing is. So if I go into Spider, and all credit to Tom Monks, my colleague, who donated this as a good example of why NumPy is the library of choice for things like this. So I've posted this. You'll be able to have a look at this in your own time as well. But let's say, so we're going to import NumPy here. Let's imagine, let's look at lists versus arrays first of all. So let's imagine we've got a list of numbers up to 1 million. This just basically generates a list of numbers up to 1 million. And then here we're doing the same thing for a NumPy array. So we've got 2 lists of 1 million numbers. Sorry, we've got a list of 1 million numbers and a NumPy array of 1 million numbers. So let's set that up. Okay, so if we have a look at those things, so here, if I open up the list, no, actually I won't do that, that'll be too slow. But you'll see that you've got the numbers 0, 1, 2, 3, 4, 5, 6, 7, etc., all the way up to 1 million. and the NumPy array, exactly the same thing, numbers 0, 1, 2, 3, 4, 5, all the way up to was actually 999,999, because we start at 0. So it's basically the numbers 0 to 999,999 in both cases. Exactly the same. It's just that one is stored as a list and one is stored as an array. And then what we're going to do is we're going to just get Python to add up the numbers in both the list and in the array. And we're going to use a function called timeIt to see how long it takes computation. Okay, so let's first of all do it on the list. So if I run this cell, actually over here. This is a special console command here. Here we go. So it's taken 4.73 microseconds to do that. Let's now have a look at how long it would take to do the same thing, exactly the same numbers being added up. Let's have a look if we were to do that in a NumPy array. Look at the difference there we've got. So we've got 403 nanoseconds essentially versus 4.73 microseconds. So an order of magnitude faster. Now, clearly in this case, both of these things are pretty quick. That's because we're not asking it to do, even adding up a million numbers isn't too much of a headache for Python, even in a list. But imagine this scaled up. Imagine you're suddenly dealing with a huge multi-dimensional array of data, and you're needing to do complex operations on these things. Now look at the time difference between doing that in a list versus doing it in a NumPy array. So you can see that for the simple examples, it's not going to make a huge difference, practically speaking. But the second you start going into anything more complex, you will very quickly run into problems, computational problems, if you're not using NumPy. It really is that much quicker. There's also, I'm not going to go through them now, but there's some other examples that Tom has put in here. If you want to run any of these examples, Tom has separated them into cells. So you simply select the cell, right click and click run cell. And then once you run that cell, simply copy and paste the percentage sign command here into your console and then push enter. And then it'll run that as a special command. And so here you're saying time, how long it takes to perform this operation to sum the Python list. So do have a look at that, because it's a huge, huge difference, and it can be a bit difficult to get your head around Python initially. NumPy initially, but that's why you do it, because it's so much easier to work with big, complex, multi-dimensional arrays, which you will work with. It just gives you such an advantage in terms of computational efficiency. It's really worth doing. Okay, enough of me talking. So, time for an exercise, which I imagine you foresaw coming. So, let's imagine you've been given data that contains 3 fields relating to patients. One represents patient ages, one the number of previous admissions they've had, and one whether they were admitted following their latest attendance to ED, with essentially a 1 indicating if they were and a 0 if they weren't. So here's your data. You haven't got this in a separate file. We'll just put it up here. This is your data. You've got your list of ages. You've got a list of number of previous admissions for each of these individuals, and a 1 or 0 to indicate whether they were admitted following their latest attendance to ED. So what I want you to do is write a program that stores the 3 data fields above in 3 separate lists, which then combines those lists into a single 2-dimensional NumPy array called data. Remember, it's going to be 2-dimensional because essentially you've got your dimension of ages and previous admissions and admitted this time, so that's your groups, and then the individual values for each of those groups. Then I want you to get it to calculate and print the mean age of patients in the NumPy array by using slicing on the appropriate row, I want you to round it to 1 decimal place. Then I want you to calculate and print. By the way, no cheating on these. So yes, you could just do it on the list. Don't do that. I want you to do it on the NumPy array. I want you to get it to calculate and print the total age of those admitted this time using slicing and a dot product calculation. So you know who's been admitted this time, and you know the ages for each of these people. So I want you to use a dot product and slicing in order to calculate the total age of everybody that has been admitted this time. And then I want you to get the code to calculate the mean number of previous admissions for those who are aged under 30 in the data. And I want you to do this a little oddly, and it's only for the purposes of this exercise. I want you to use slicing and assume the list is static. And by that, I mean, you don't need to worry about doing anything clever here. Oops. Sorry. Okay, sorry. So don't do anything clever here. All you're going to do is you're going to assume this is a fixed list of ages. So you just want to grab those in the list that are under 30. In other words, the first 7 values. Okay, so you're going to assume that this is fixed and it'll always be like that. In reality, you would not do that. This is just a fabricated example to get you to practice using slicing. So basically grab the 7 initial age values and calculate the mean number of previous admissions for those 7 entries. Okay. So I'm going to give you half an hour to do that. So you've got till 3 o'clock. You, as always, are very welcome to work in groups or individually, but please do shout if you're stuck. Any questions about any of that? No? Great. Okay. In which case, see you at 3. As I do shout if you're stuck, and I do encourage you, if you aren't feeling that comfortable, you want to bounce this idea, your ideas off other people, I would encourage you to work in groups where you can, just to help you with this, because it's not a massively difficult exercise, but NumPy itself can be quite tricky to get your head around. So please don't be disheartened if you're finding this a bit odd. NumPy is one of the most difficult things that people have to get their head around in early Python, but it is also one of the most useful. So it's well worth sticking with it. Great. See you in half an hour, guys.